So there's similar characteristics that we spoke about in terms of lift. So if we were to reduce or increase the primary chilled water speed, that will have implications on how hard that chiller needs to run with the same thermal load on the system. But really, the primary chilled water pump should be there to deliver enough water through that chiller so that it's able to hit the set point. And our chilled water leaving temperature set point of, say, 6 degrees Celsius. Really, what that's doing there is providing enough water. In this system as well, it's also looking at providing enough differential pressure, generating enough pressure to get the water to all of the air handling units in the system. So where it's a primary only system, it's got the dual jobs of providing enough flow through the chiller so that we're hitting those minimum flow rates, but then also enough pressure to distribute that to the field and get that water back. Where we get a more complicated system and it's secondary and tertiary systems, then really the job of the primary chilled water pump is just to deliver enough of that water through the chiller. There is optimization opportunity there in terms of pressure and flow resets that can be done. So when the chillers are operating at part load, as the example with condenser water, we can start to reduce that flow rate right down to the minimum. And that can be helpful to actually increase the delta T across the chiller. So if we get into some territory where we're actually supplying too much chilled water to the chiller, we can have a low delta T. So the return temperature or the return temperature to the chiller might be 7.5 degrees Celsius and the leading temperature is 6 degrees. In an ideal world, we'd want to reduce that flow to get that up around 12 degrees return and 6 degrees leaving so that we've got a higher delta T across the chiller. Savings there then comes twofold, really.